Maker. I am Ranjan Kumar Kalindi. As we have completed our digital electronics chapter one short video, there we have covered all the syllabus and we have discussed all things about digital electronics. So today we are going to see some related question which are important for your exam. Whatever exam you are preparing, like BL, ECIL, WHALE, HAL, ISRO, whatever PSU and anything, there you have digital electronics subject. For that these questions are important. Okay, so for PDF and updates, you can join our Telegram channel. This is my Telegram channel name. You can join this one directly using Telegram, or just go to description box. There you will get this Telegram link and this WhatsApp channel link. Just join this one. Here you will get PDF notes and class update. Whatever things material regarding is there, you will get here only. Okay, so we will discuss some question related to digital electronics. Found the output. Okay, so input is what? Input is x is here. Okay, so here we can put x, this is x, and this is what? NOT gate. Okay, here input is x, after NOT gate the output will be x complement. Okay, now this is what? XOR gate. So if you see XOR gate, for XOR gate, suppose A, B, we have two input XOR gate. Okay, then this is what? 0 0 0 1 1 0 1 1. We have four condition for XOR gate. If both are same input, then output will be 0. Okay, and if any one is high, then output will be high. This is the truth table for XOR gate. Okay, now see, we have x and x bar as a input. So if we put x equal to 0, if we put x equal to 0, then x bar means x complement means what? X complement means 0 means 1, x complement means 1 means it will do complement of 0, so complement of 0 is what? 1. So when a is 0 and b is, this is what? This is a and this is b, like that you can consider as an input. So a is 0, and b is 1. So in this case output is what? Output is 1. Okay, now if we put a is x equal to 1, and in that case we have b as a x bar, so 1 complement is what? 0. So in this case also a is 1 and b is 0, then output will be 1 only. So output will be 1. So both case output we are getting 1. So here y value is what? Y value is 1. Option A is your right answer. Okay, the simplified form of, we have AC bar plus ABC bar. Okay, from here we can take A and C bar as a common. Then this is what? 1 plus B. We can write like this. And we know this thing. If 1 plus A is there, then the output is what? 1 only. So from here AC bar, and this will become what? 1. So this is AC bar will be your answer, option B. Okay, like that you need to remember some Boolean points. Boolean algebra formula is there, like 1 plus A is 1, then 1 dot A is A, then 1 sorry 0 plus A is what? A, then 0 dot A is what? 0. So like that some Boolean formula is there, you need to remember that one to solve this kind of equation. Okay, what is the minimum number of NAND gate required to implement A plus A B bar plus A B C bar? Okay, now we can solve this one. We can take A as a common. So A is a common, we can write 1 plus B bar plus B C bar. Okay, and right now we have seen 1 plus anything is there, it will become 1 only. Okay, so we can write here A dot this one, what? This will become 1, because 1 plus something is there is 1. So A is your answer. So A is your answer. We need to required minimum NAND gate. So only one input is there. So zero NAND gate required. No need of any NAND gate to implement this one because only one input is there, A. So option A is your right answer. Zero NAND gate required to implement this one. The logic function implemented by a multiplexer. So this is a multiplexer 4 into 1 mux we have. We need to find output F, which logic it is going to follow. So here they are saying ground implies a logic 0. Means ground means what? This is what? This is the value of 0. So 0, we have this one. This is not gate. So not gate. After not gate, the output will become 1 here. Then again after not gate, it will become 0 here. Because the not we know, not means complement. So 0 complement is 1, 1 complement is 0. Now from here we can write I0 is equal to what? This is 0. Then I1 is coming like this. So I1 is 1 only. I2 is also, it is coming like this. So it is 1. And I3 we have from here. So this is 0. Okay, we got the value of I0, I1 and I2, I3. Now this is mux. So we have two select line. This is S1, S0, that is P and Q. So we have four conditions 0, 0, 0, 1, 1, 0, and 1, 1. Like that, we have four conditions. Okay. So now, if you see, this is P and this is Q for 0, 0, 0, 1, 1, 0, and 1, 1. Okay. We have four conditions and the output, that is what? F. Output means what? Output is F. F, it will select according to the select line. This is the function of a multiplexer. The output is going to select or it will decide according to the select line condition. Suppose it is 0, 0. So in 0, 0 case, it is going to select I0. Okay. That is what? That is 0. So, and the next condition when select line will be 0 and 1, 0 and 1. In this case, it is going to select I1 as an output. Okay. And it is what? It is 1. So when 1 0 is there, then output will be your I2. I2, that is what? 1. And 1 1, in 1 1 case, it will be I3, that is your 0. Okay. Now if you see this truth table, okay. If you see this truth table is belong to what? This truth table is belong to XOR gate. Okay, this truth table is belongs to XOR gate. Just now we have discussed in a first question. I think the truth table is same as a XOR gate. So XOR gate. So it will be, we can say option D. This one function output will be XOR of P and Q. Okay, this is your answer. Option D. The full adder is dash input and dash output combinational circuit. So adder is a combinational circuit we know already. So adder, if we talk about adder, then we have half adder, half adder and full adder. Okay. We have half adder and we have full adder. So in half adder we have two input line A and B. We have two input and we have two output, that is sum and carry. Okay, this is what half adder. And if we talk about full adder, then in full adder we have three input and two output. Three input is what? A and B, and one is carry in, and output will be your sum and carry. So this is what full adder. So in full adder we have three input and two output. Okay, we have three input and we have three input and we have two output. Okay, just a second. So in adder we talked about half adder and full adder. Okay, so in half adder we have two input and 2 output, that is your AB, and sum and carry. Like that, in full adder we have 3 input, that is A, B and carry in, and output will be your sum and carry. Okay, this is your half adder, this is your full adder. So in question they have asked for full adder. So in full adder, 3 input is there and 2 output is there. So option D is your right answer. In a parallel shift register and serial shift register, the number of clock pulses required to enter a byte is dash and dash respectively. So they are asking about parallel shift register and serial shift register. So we have shift register. If we talk about shift register, so we have 4 kind of shift register. First in serial in, serial out, serial in, serial out, serial in, parallel out, then parallel in, serial out, and parallel in, parallel out. 4 kind of shift register we have in a digital electronics. So in a parallel shift register, the number of clock pulses required in a parallel. First we talk about in parallel, then in a parallel shift register, we need 8 bit, means here they have asked about a byte. Okay, a byte is what, one byte is equal to 8 bit. So for 8 bit we need only one clock pulse in a parallel circuit. Okay, we need only one clock pulse for 8 bit data. And for serial, or for serial shift register, for a byte, that is 8 bit, for each bit we need each clock pulse, means 8 clock pulse we required for 8 bit. Okay, we required 8 clock pulse for 8 bit data. So from here it will be, answer will be your B, 1 and 8, 1 clock pulse and 8 clock pulse required for a parallel shift register and serial shift register. Okay, if the present state is 0 and the next state is 1, then if the present state is 0 and next state is 1, then what is the condition for a JK flip-flop? It is given in an option, you can say it is what, JK flip-flop. So if you talk about excitation, okay, excitation table of JK flip-flop. Okay, if you see excitation table for JK flip-flop, then it will be Qn, that is your present state, and Qn plus 1, that is your next state. So for that, the condition for JK is what? So we have 0 0, 0 1, 1 0 and 1 1. Okay, for condition is there. In that case, when present state and next state, when present state is 0 and next state is 0, in this case J is 0 and K will be don't care. And when it is 0 and 1, in this case it is 1 and it is don't care. When it is 1 and 0, then in this case it is don't care, it is 1. When it is 1 1, then in this case it is don't care, and this will be 0. Okay, so here they have asked about present state is 0 and next state is 1, then in this case J will be 1 and K will be don't care. Okay, J will be 1 and K will be don't care. So your option 1 is A is a right answer. Okay, when we will talk about JK flip-flop, then some points you need to remember about JK flip-flop, like race around condition. Generally question they are asking about race around condition. Okay, race around condition, in which flip-flop race around condition occur. So answer will be JK flip-flop. In which case race around condition, in which flip-flop race around condition occur, so it will be JK flip-flop. And what is the condition for this? When J and K both are 1 1, in that case it will be toggling, in toggling state. So that is your race around condition. to overcome a race around condition, what flip-flop we are using? So that is your master flip-flop. Okay, master flip-flop, master slave. Okay, master slave flip-flop is used to overcome the race around condition. Okay, just remember this 2 point. Okay, this 2 point you need to remember. The two's complement of the binary number, we have 0, 0, 1, 1, 1, 1, then 0, 0. This is the binary number. Now we need to convert, we need to find two's complement. So for two's complement, first we need to convert this thing in a one's complement. So one's complement, how we are doing one's complement? One's complement is nothing, just you need to do a complement of a number. Like it is 0, so make it 1, 0, 1, 1 means 0, 0, 0, 0. Then again 0 means 1, 0 means 1. Now for 2's complement, we need to add 1 here. So just add 1. So it will be 1 plus 1 is what? 10. That is a 0. Now carry is what? Carry is 1. Then again 1 plus 1 is 10. That is 0. Again it will go carry here. So 1 plus 0 is what? 1. Now 0, 0, 0, 1, 1. So this is your 2's complement. Okay, this is your 2's complement. So here you can say your answer will be option A, right? Which flip-flop is used to make all type of shift register? Okay, which flip-flop is used to make all type of shift register? So we have D flip-flop. We have D flip-flop to use all type of shift register. Using D flip-flop, we can make all type of shift register. All type of shift register means serial in, serial out, serial in, parallel out we can design, then parallel in, serial out, and parallel in, parallel out we can design using D flip-flop only. Okay, using D flip-flop we can design all the shift registers. Okay, binary representation of the hexadecimal, we have 4a as a hexadecimal. Okay, this is hexadecimal. Now we need to convert this thing in a binary form. So binary form is nothing but we need to do uh, binary in the term of 0101 with a 4 bit. Okay, 4 bit. So if you take a is what? A is nothing but a is 10. So 10 how we are writing in a binary? 1010. Then 4 how we are writing in a binary? This is 0100. So this is the representation of a 4a. Okay, that is your this one. Option D is your right answer. Okay. A digital circuit has 3 input line, 1 enable line, and 8 output line. The circuit will call. So we have, okay, this is the circuit they are saying like they have 3 input line. Okay, they have 3 input line and 8 output line. Okay, 8 output line. This is O0, O1, and this is O7. 8 output line is there. In that I0, I1, I3 input line is there, and one enable line is also there. So it is called 3 into 8 decoder. Okay, decoder. This is called what? 3 into 8 decoder. In a decoder circuit, we have n decoder. If we are talking about n bit decoder, then it will be, it has an input line and 2 to the power an output line. Okay, just remember. If you are talking about 3 into a 8 bit means 3, um, n is your 3. Okay, so n is your 3 means 2 to the power n, 2 to the power 3 is what? 8. So 8 output line will be there for a decoder circuit. Like that, if you are talking about encoder circuit, okay, if you here from here answer will be your decoder. If you are talking about encoder circuit and suppose we have 4 into 2, 4 into 2 decoder, then we have 4 input and 2 output with 1 enable line. This is what encoder. Encoder. Here encoder in this case 2 to the power n input line will be there. Input line. Okay. And n output line will be there. Okay. Just opposite encoder and decoder. Now from this multiplexer, if you talk about multiplexer, if you talk about mux multiplexer, suppose it is what 4 into 1 multiplexer. Mux means what? Multiplexer means many input and single output. That is your multiplexer, many input and single output. So we have 4 into 1 multiplexer, so 4 input and 1 output, and this will be output will be decided according to the select line. So 4 input is there in this case, 2 select line will be there. Okay, so if it is n, then this is your 2 to the power n. Okay, just remember this thing. So this is what? This is your mux, that is multiplexer. So in multiplexer, if n select line is there, okay, if n select line is there, so 2 to the power n input line will be there, and output is always 1 only. Now for demultiplexer. For demultiplexer, again, if it is 1 into 4, demultiplexer means 1 input, always it will be 1 input and many output. 4 is there, so 4 output will be there, and again 2 select line. Okay, and here also it will decide if n is select line. Okay, if n is select line, n number of select line is there, then 2 to the power n output line will be there in demultiplexer. That is called demux. Okay, just remember this point for your point of view of exam. Write the simplified equation for the given K-map. We have K-map, we need to find the equation. So, you know K-map also. So, how you need to do? You need to do pair. First, we need to find 8 ones. If 8 ones is not there, we need to go for quad, that is 4 pair. So, here you can see this one we can make as a 1 pair, and from here we can make 1 quad. Okay, so we have 2 quad in a K map, in this K map, and from here we can make equation like this. So this is what this is from here, this is output y equal to, from this section we can see, from first this side, if you talk about this side, then your here common thing is what? This one and this one. So from here we can write 1 is what? 1 is your B2. This is what? Here B2. Okay. Here you can see 0 0 means this is B3 and B2. 0 means bar. Okay. Here also B3, B2, 0 means bar, and B2 will be like this. Then 1 1, 1 1 means B3, B2. Then here B3, B2, and 0 means bar. Like this you need to put. So from here you can see 1 1, that is B2 is common in both. B2 is common, so we can write here B2, and from this side. Now from this side common thing is 0. Okay, common thing is 0. 0 means B1, B0 bar bar, then B1, B0, 0 means here bar. So B1 bar is common, so we will write here B1 bar. Now plus. Now we are now come to this quad. So in this quad, first we will see from this side. From this side, which one is common? This 0 is common and this 0 is common. 0 0 means what? B2. B2. 0 means bar. Okay. 0 means bar. Now from this side, which one is common? From this side, here this one and this one. One is common. 1 means what? Here this is what? B. This one is B1, B0, B1, B0, and this is bar. So here B1 is common. So we will write here B1. So your output expression will be your this one. So which is related to, you can see option A is matching with this one. So we can write this one B1 bar B2 plus B2 bar and B1, like that also we can write. So option A is your right answer. The 4-bit gray code for decimal number 5. We have decimal number 5 here. We need to first convert this thing in a binary form. So 4-bit they are asking. So 4-bit representation of this 5 is what? That is your 0101. This is what? Binary number. So 5 we know binary, this one. Now we need to find the gray code conversion. Gray code we need to find. So write like this 0101. Okay, this is your binary. So whenever we are going to convert a gray code or gray code to binary or binary to gray code, then we require XOR operation we need to do. XOR operation again if we see truth table, which we already seen 2 times in a previous question also, 000110 and 11. Okay, so in this case it will be 0, it will be 011. Okay, now we need to put XOR operation here. First this MSB bit we need to write as it is. This is 0. Now between 0 and 1 we need to put XOR operation. So 0 and 1. 0 and 1 is what? Output will be 1. So here it will be 1. Again 1 XOR this 1 and this 0. 1 XOR 0. So 1 is here. 1 and 0 is what? Again it is 1. Again we need to put XOR here 0 and 1. So 0 and 1 is what? 1. So this is 1. Now this is your what? This is your gray conversion. This is your gray value. That is option A is your right answer. Suppose if they will ask convert gray code to binary, we have 0 1 1 1. This is your gray. Okay, this is your gray conversion, gray representation. We need to find the binary. So as it is, you need to write MSB, that is 0. Now we need to apply here also XOR, but we need to apply like this. This is 0 and 1, 0 and 1, this 0 and this 1. 0 and 1 is what? 0 and 1 is 1. Again from this 1 to this 1 you need to apply XOR operation. This one and this one. So 1 XOR 1, 1 XOR 1 is what? 0. So here it will come 0. Now again 0 and 1. 0 and 1. 0 XOR 1. 0 XOR 1 is what? 1. So this is your binary representation which is matching with this one. So like this you need to do gray to binary and binary to gray conversion. Okay. Which logic family is used for high speed applications? So ECL, that is your emitter coupled logic, is used for high speed application because the mm, propagation delay time is 2 nanosecond. Among the all it is very less. Propagation delay time is very less. That's why ECL is the highest speed application among the all logic family. Dynamic RAM, that is DRAM, is slower than SRAM, static RAM, because of what? So if we talk about memory, so we have memory, one is RAM and another is ROM. Okay, RAM is called volatile memory. Just remember this thing. This is what? Volatile memory, and this is non-volatile memory. Okay, sometime they will ask which memory is a volatile memory. So RAM is a volatile memory. Now further, RAM have two type, that is your SRAM, static RAM, and this is dynamic RAM. Okay, RAM is what? Random access memory. ROM is read-only memory. So SRAM, in SRAM, it uses flip-flop. It uses flip-flop to store. Okay, it uses flip-flop to store SRAM. And if we talk about DRAM, then DRAM it uses capacitor. It uses capacitor to store. SRAM uses flip-flop, and it capacitor uses DRAM uses capacitor to store. That's why it required refreshing. It required refreshing. Okay, it required refreshing. DRAM, it uses capacitor, that's why it required refreshing, and that's why it required refreshing. Because of that only it becomes slower. Okay, it becomes slower. And here it not required refreshing because it using flip-flop, that's why it is not required refreshing, that's why it is faster. Okay, just remember this thing. So it is slower. Why it is slower? Because it required refreshing. Because it required refreshing. DRAM required refreshing. That's why it is slower than SRAM. Okay, this is your answer. Number of unused states in 4-bit Johnson counter. Johnson counter is also called as a ring counter. Okay, Johnson counter is also called a ring counter. Johnson counter is also called a ring counter. So if you calculate total number of states in counter, total number of states in counter, that will be your 2 to the power n. Okay, here n is what? N, they are asking for 4-bit. So 2 to the power 4 is equal to what? 16. Okay. And if you see total state of Johnson counter, total states of Johnson counter, that will be your 2 into n, that is 2 into 4 bit means 4, that is your 8. So we have unused state, we have unused state is how much? This is total is 16 and Johnson is 8. So 6 minus 8, 16 minus 8, that is equal to 8 is your right answer. So the number of unused state in 4-bit Johnson counter is 8 only. The SR latch is an example of SR latch. So latches we have latches and flip flop. We have latches and flip flop. So latches and flip flops are a basic element to store one bit of basic element to store one bit of data. Okay, one bit of data. That's why it is called. That's why it is called one bit memory element. One bit memory element. Okay, that's why it is called one bit of memory element. Latches and flip-flop are a basic element to store one bit of data. That's why it is called one bit of memory element. Okay, and we have 4 type of latches. First one is what? SR latches, JK latches, D latches, and T latches. Okay, so in a question they have asked about SR latches. If they will ask for JK latches also, then it is also one bit memory element. D latches also one bit element, and T latches then also it is one bit element. Okay, similarly flip flop also a one bit memory element, and it has 4 type of flip flop. Same it is SR flip flop, then JK flip flop, then D flip flop, and last one is your T flip flop. Okay, now one more thing you just remember, which is very important. Not sometime, generally in a question they will ask latch is asynchronous. Okay, latch is asynchronous. Just remember this thing, and flip flop is a synchronous. Okay, this is the difference between latch and flip flop. So from here, one bit of memory element. Which among the given expression is the product of sum? So we have two things. SOP. SOP is what? Sum of product. Sum of product. SOP and POS. POS is product of sum. Okay. So sum of product means we have we have some product and their sum is called sum of product. That is, if you see AB and CD. So we have two product and their sum will called sum of product. This is what sum of product. Like that, if we have A plus B and C plus D, then we can say this is two sum is there. So product of sum, there will be product. So product of sum. This is the example of product of sum. So two sum is there, their product. So likewise, in a they have asked product of sum, that is POS. So in an option you can see only this example is related to POS. There will be two sum and their product is there, and rest of all are there is this one is your SOP, that is sum of product. This is also okay. This one only. This is the example of SOP, and this is the example of POS. Option A is your right answer. Okay. When a JK flip-flop is constructed from a SR flip-flop, okay, we have SR flip-flop, you means we need to design JK flip-flop. Okay, JK flip-flop is constructed from SR flip-flop. So first you design SR flip-flop. Okay, this is what? This is your S and R flip-flop. This is your Q complement and this is your Q. And this input will go here and this will go here. This is your SR flip-flop. Now for JK, we need to what? JK flip-flop we need to construct here. So for JK, what we are doing here, we will put AND. So like this here also, this is your AND gate. Like this we need to follow. So this is your J and this is your K. Okay, and this will go like this here, and this will go like this here. Okay, and we need one clock pulse. So this is your clock pulse. Okay, so this is the design what they are asking in a question. So from here you can say for S is what? S is J and Q bar. So we can write S is what? JQ bar, and R is like that K and Q. So from here option D is your right answer. Okay, from option we can write S is JQ bar and R is KQ. So option D is your right answer. Okay. The number of comparator required in a 4-bit comparator type of ADC. Okay, analog to digital converter comparator. So for n bit, if we talk about n bit comparator type ADC, okay, for n bit comparator type of ADC, we need number of comparator required is what? Required comparator is what? 2 to the power n minus 1. Okay, so here n is what? N bit, we have 4 bit, so 4 is what? 2 to the power 4 minus 1, that is equal to 16 minus 1, or 15 comparator will required for 4-bit comparator type ADC. So option B is your right answer from here. Okay, now for this question, which of the following logic gate is used for parity generator? So this one you need to answer and keep this answer in a comment box. You need to comment this answer in a comment box. Okay.